Max Planck's groundbreaking work in the field of physics began with a problem that had perplexed scientists for years: the issue of blackbody radiation. A blackbody, in physics, is an object that absorbs all incident electromagnetic radiation, regardless of frequency or angle of incidence. It also emits radiation, and the spectrum of this emitted radiation depends on the temperature of the object. At the time, scientists, including Lord Rayleigh and James Jeans, had proposed a theory to explain the radiation emitted by a blackbody. Their model, based on classical physics, suggested that the energy emitted by a blackbody increased infinitely as the wavelength of the radiation became shorter, leading to what became known as the ultraviolet catastrophe. This problem arose because the predictions of the model failed to match experimental data at high frequencies, where it suggested that blackbodies would emit infinite energy. The actual observed radiation, however, tapered off at higher frequencies, indicating that the classical model was fundamentally flawed. Planck's approach to solving this problem was revolutionary. At the time, the laws of thermodynamics and classical mechanics were dominant, but they were inadequate when it came to explaining the behavior of radiation. Instead of relying solely on these traditional methods, Planck took a bold step forward. In 1900, he proposed that the energy of the electromagnetic radiation emitted by a blackbody was not continuous, but instead came in discrete units, or quanta. This concept was alien to classical physics, which viewed energy as a continuous flow. Planck's insight was that energy could only be emitted or absorbed in fixed amounts, which he described as multiples of a fundamental unit. This was a radical departure from classical theories. Planck introduced the idea that the energy of a single oscillator, such as those within the atoms of the blackbody, could only take certain discrete values. These values were proportional to the frequency of the radiation, and this proportionality was determined by a constant now known as Planck's constant. The energy, according to Planck, was given by the formula E equals hc dot F, where times E times is the energy of the radiation, asterisk H times is Planck's constant, and times F times is the frequency of the radiation. This equation became the foundation for quantum theory. Planck's constant, asterisk H, asterisk, had a value of approximately 6.626 times 10, negative 34, joule seconds, a number so small that it was almost unimaginable. But it would go on to become one of the most important constants in all of physics. This idea of energy quantization was not an attempt to explain all phenomena in the universe, but rather to resolve the specific problem of blackbody radiation. However, Planck's solution had far-reaching consequences that no one, not even Planck himself, could have foreseen. His work showed that energy at the microscopic level behaves very differently from what classical physics predicted. Instead of flowing smoothly, energy exists in small, discrete packets. This was the first step toward the development of quantum mechanics, a theory that would go on to revolutionize our understanding of the atomic and subatomic worlds. Planck's quantization hypothesis was initially met with resistance. Many physicists at the time were deeply entrenched in the classical worldview, and the concept of quantized energy seemed more like a mathematical trick than a physical reality. Planck himself was reluctant to fully embrace the implications of his discovery. He introduced the idea as a mathematical assumption to make the radiation law work, rather than as a profound shift in our understanding of nature. However, as experimental evidence continued to accumulate in favor of the quantization of energy, it became clear that Planck's hypothesis was not just a mathematical curiosity, but a cornerstone of a new physics. One of the most striking consequences of Planck's work was its impact on the concept of temperature. In classical thermodynamics, temperature was seen as a measure of the average energy of the particles in a system. However, Planck's theory showed that temperature was not simply a measure of energy, but was linked to the distribution of quanta within a system. This gave rise to new concepts in statistical mechanics and the understanding of entropy. For the first time, scientists were able to reconcile the behavior of macroscopic systems, like the temperature of a gas, with the microscopic behavior of particles. The birth of quantum theory was not only a triumph for Planck, but also set the stage for future discoveries that would further unravel the mysteries of the atomic world. One of the most significant developments that arose directly from Planck's work was Albert Einstein's explanation of the photoelectric effect in 1905. Einstein took Planck's idea of energy quanta and applied it to the interaction of light with matter. He proposed that light itself was quantized, coming in particles called photons. This explanation not only confirmed the particle-like nature of light, but also provided experimental support for the notion of quantization, which was still considered a strange and untested idea by many physicists at the time. Another key figure, influenced by Planck's work, was Niels Bohr. Bohr's atomic model, developed in 1913, relied heavily on the idea of quantization. He proposed that electrons in atoms could only occupy specific energy levels, and that they could absorb or emit energy only when they moved between these levels. This model explained the spectral lines of hydrogen and provided further evidence of the quantized nature of energy. Though Planck himself did not fully realize it at the time, his work laid the foundation for what would become one of the most successful and influential theories in the history of science, quantum mechanics. The theory would continue to evolve with contributions from scientists like Werner Heisenberg, who formulated the uncertainty principle, and Erwin Schrödinger, who developed wave mechanics. But it was Planck's quantum hypothesis that initiated this profound shift in our understanding of the physical world. Max Planck's contributions went beyond just his scientific discoveries. His work provided a new lens through which to view the universe, one that embraced uncertainty and the limits of human knowledge. Planck was aware that his work had opened a new chapter in physics, but he was also conscious of the fact that this new chapter was only just beginning. Despite the initial resistance to his ideas, Planck remained steadfast in his belief that the laws of physics were not bound by the classical, deterministic worldview. Instead, he recognized that the universe was governed by principles that were fundamentally probabilistic and that the true nature of reality could not be understood through classical reasoning alone. Today, the impact of Planck's ideas is felt across every corner of modern physics, from the development of semiconductors and quantum computing to our understanding of the behavior of light and matter at the smallest scales. The study of quantum mechanics has led to groundbreaking technologies such as lasers, MRI machines, and GPS systems. And yet, despite all these advances, the full implications of quantum theory remain a subject of fascination and mystery. What Planck started with his discovery of quantized energy continues to shape the way we think about the universe on the most fundamental level. In conclusion, Max Planck's biggest idea was not just the quantization of energy, but the recognition that the world of the very small is governed by a different set of rules than those we experience in our everyday lives. His work signified the birth of quantum mechanics, a theory that has become one of the most powerful tools in physics. Planck's boldness in proposing a radically new approach to understanding radiation paved the way for the discoveries of Einstein, Bohr, Heisenberg, and many others. His legacy lives on in the countless technologies and insights that have emerged from his initial breakthrough, forever changing the landscape of modern science. Max Planck's idea of quantized energy was not only a breakthrough in understanding blackbody radiation, but also marked the beginning of a profound shift in our comprehension of the physical universe. This shift had far-reaching consequences for the development of modern physics, influencing a range of scientific disciplines and altering the way we understand energy, matter, and the fundamental nature of reality itself. The core of Planck's hypothesis was his assertion that energy is not continuous, but instead comes in discrete packets or quanta. This idea, introduced in 1900, emerged from Planck's efforts to solve the problem of blackbody radiation, which had baffled scientists for decades. Before Planck, it was widely accepted that energy could be transferred in a continuous manner. However, this assumption led to the paradox of the ultraviolet catastrophe, where classical theories predicted that blackbodies would emit infinite amounts of energy at high frequencies, which clearly contradicted experimental observations. Planck's solution was revolutionary. He suggested that energy could only be emitted or absorbed in fixed amounts, proportional to the frequency of the radiation. This insight marked the birth of quantum theory, even though Planck himself did not fully grasp the implications of his discovery. He introduced a mathematical formulation to explain the emission of radiation by blackbodies based on the assumption that energy is quantized. The energy, according to Planck's equation, is given by E equals hsc.f, where times E times is the energy of the radiation, asterisk h times is Planck's constant, approximately 6.626 times 10, negative 34 joule seconds, and times f times is the frequency of the radiation. This equation, though simple, would go on to become one of the most important relationships in all of physics. One of the most significant consequences of Planck's discovery was the birth of quantum mechanics. Planck's work set the stage for subsequent breakthroughs by other physicists. Albert Einstein, building on Planck's ideas, used the concept of quantized energy to explain the photoelectric effect, where light striking a metal surface causes the emission of electrons. This experiment confirmed that light, once thought to be a continuous wave, also behaved as though it were made up of discrete particles, or photons. This insight helped solidify the idea that energy could be quantized in all forms, not just in the case of blackbody radiation. The next major development in the wake of Planck's work was the Bohr model of the atom. Niels Bohr, in 1913, adopted Planck's concept of quantized energy to explain the structure of the atom. Bohr proposed that electrons in an atom could only occupy specific energy levels, and that they could absorb or emit energy only when they moved between these levels. The energy associated with these transitions was also quantized. In accordance with Planck's idea, this model successfully explained the spectral lines of hydrogen and was an important step in the development of quantum theory. The introduction of quantized energy also led to the development of wave-particle duality, a key concept in quantum mechanics. The idea that light could behave both as a wave and as a particle was one of the central tenets of quantum theory, and it emerged directly from the work of Planck and Einstein. This duality would later be incorporated into the broader framework of quantum mechanics, where particles like electrons and photons are described by wave functions, which encode the probability of finding the particle in a particular state or location. In addition to its theoretical significance, Planck's idea of quantized energy had profound implications for technology. The development of quantum mechanics led to the creation of technologies that are integral to modern life, such as semiconductors, lasers, and magnetic resonance imaging, MRI. These technologies rely on the principles of quantum mechanics, which are based on the quantization of energy. For example, semiconductors, which are the building blocks of modern electronics, work by exploiting the quantum properties of electrons in materials. Similarly, lasers, which are used in everything from communications to medicine, depend on the controlled emission of photons in discrete amounts, a concept rooted in Planck's quantization of energy. One of the most remarkable aspects of Planck's discovery is that it led to a new way of thinking about the very nature of reality. Classical physics, which had dominated the scientific worldview for centuries, assumed that the universe was deterministic and that objects behaved in predictable, continuous ways. Planck's introduction of quantization, however, implied that at the microscopic level, the laws of physics are fundamentally probabilistic. Instead of energy flowing smoothly and predictably, energy exists in discrete amounts, and the behavior of particles is governed by probabilities rather than certainties. This was a profound shift in our understanding of nature, and it laid the groundwork for the development of quantum mechanics, a theory that describes the behavior of particles at the atomic and subatomic scales. As the 20th century progressed, the quantum revolution continued to unfold, with physicists such as Werner Heisenberg and Erwin Schrödinger further developing the mathematical framework of quantum mechanics. Heisenberg's uncertainty principle, which states that it is impossible to simultaneously know both the position and momentum of a particle with absolute precision, was one of the key results of the new quantum theory. Schrödinger's wave equation provided a mathematical description of how quantum states evolve over time, further cementing the probabilistic nature of quantum mechanics. Despite the success of quantum mechanics in explaining the behavior of particles, some aspects of the theory remain mysterious. For example, the question of how the probabilistic nature of quantum mechanics reconciles with the deterministic nature of classical physics is still an open question in physics. Similarly, the interpretation of quantum mechanics and its implications for our understanding of reality continue to be the subject of debate among physicists and philosophers. The idea that particles can exist in multiple states at once, known as superposition, challenges our intuitions about the nature of reality and the limits of human knowledge. Max Planck's discovery of energy quantization was a small but crucial step in a larger intellectual journey that would reshape our understanding of the universe. Planck's work was the catalyst for the development of quantum mechanics, a theory that would go on to revolutionize fields ranging from particle physics to chemistry to computer science. His ideas have not only shaped the course of physics but also paved the way for technological innovations that have transformed the modern world. Planck's work remains a testament to the power of bold thinking and the capacity of science to uncover the hidden truths of the universe, even when those truths challenge our most basic assumptions about reality. In summary, Max Planck's idea of quantized energy was not only a solution to the problem of blackbody radiation, but also the beginning of a new era in physics. His work laid the foundation for quantum mechanics and opened up new realms of scientific inquiry that have led to groundbreaking discoveries and technologies. While Planck's initial hypothesis was met with skepticism, it ultimately changed the way we view the universe at the smallest scales. The legacy of Planck's work continues to influence science and technology to this day, and his contributions remain a cornerstone of modern physics. Max Planck's introduction of quantization not only solved the specific problem of blackbody radiation, but also marked the beginning of a new era in physics that would fundamentally reshape our understanding of the universe. The concept of quantized energy stood in stark contrast to classical physics, where energy was seen as a continuous entity that flowed without restriction. Planck's radical departure from this traditional view paved the way for the development of quantum theory, a framework that would eventually lead to groundbreaking discoveries in the realm of atomic and subatomic particles. The notion that energy could only be emitted or absorbed in discrete packets, which Planck described as quanta, was a game-changing insight. One of the central concepts Planck introduced was Planck's constant, denoted as times h*, a tiny number with profound implications. The value of this constant is approximately 6.626 times 10 negative 34 joule seconds, and it sets the scale for the quanta of energy. According to Planck's equation, E equals hc dot F, energy is directly proportional to the frequency of radiation. This relationship made it clear that the energy of electromagnetic radiation could not be arbitrary, but had to exist in fixed, quantized amounts. This insight was a fundamental shift in understanding the behavior of energy and matter at microscopic scales. The quantization of energy was first introduced to explain blackbody radiation, but its consequences rippled across the landscape of physics, influencing the development of multiple fields. from thermodynamics to atomic theory. In the case of blackbody radiation, classical physics had been unable to explain why objects at higher temperatures did not emit infinite amounts of radiation at short wavelengths. Planck's hypothesis resolved this paradox by showing that at higher frequencies, radiation energy became less likely to be emitted in continuous amounts. Instead, it was restricted to discrete packets of energy, a concept that Planck first introduced as a mathematical assumption, but this idea quickly became recognized as a fundamental feature of the physical world, one that had broader implications than anyone could have anticipated. This concept of quantization in energy would go on to shape the theory of quantum mechanics, a framework that completely altered our understanding of the microworld. The idea that the properties of particles, like their energy, could only take specific, discrete values led to a re-evaluation of how particles behave and interact. Unlike classical mechanics, which assumed that physical properties such as position and momentum could take any value, quantum mechanics showed that these quantities were governed by probabilities. This realization fundamentally changed the way scientists viewed the behavior of matter on the smallest scales. As quantum theory began to take shape, other key figures such as Albert Einstein, Niels Bohr, and Werner Heisenberg expanded upon Planck's work and refined it into a comprehensive theory of quantum mechanics. Einstein's work on the photoelectric effect in 1905, which used Planck's concept of energy quanta, demonstrated that light itself could be quantized and composed of particles called photons. This idea of wave-particle duality, where light and matter could exhibit both wave-like and particle-like properties, would become a cornerstone of quantum mechanics. One of the central features of quantum theory is the probabilistic nature of particles. In classical mechanics, it was assumed that we could know the exact position and velocity of a particle at any given time. However, quantum mechanics, starting with Planck's work, demonstrated that at the quantum level, particles do not have definite positions or velocities, but instead exist in a state of probability. This idea was formalized in Heisenberg's uncertainty principle, which posited that there is a limit to how precisely we can measure certain pairs of physical properties, such as a particle's position and momentum, simultaneously. Another key development that arose from Planck's work was Niels Bohr's atomic model. Bohr applied the idea of quantized energy to the structure of the atom. He proposed that electrons could only occupy specific energy levels and that they could absorb or emit energy only when transitioning between these levels. This model successfully explained the spectral lines of hydrogen and made predictions that were later confirmed experimentally. Bohr's work showed that atoms are not just simple collections of electrons orbiting a nucleus, but rather their structure and behavior are governed by quantum principles. The importance of Planck's contribution cannot be overstated. His work laid the foundation for the entire field of quantum mechanics, a theory that would not only explain the behavior of atomic particles, but would also lead to the development of many modern technologies. The advent of quantum mechanics gave rise to innovations such as transistors, lasers, and the technologies behind modern electronics and computers. Without Planck's initial insight into the quantization of energy, none of these breakthroughs would have been possible. Furthermore, the implications of quantum mechanics extend beyond technology. They also challenge our fundamental understanding of reality itself. Concepts such as superposition, where particles can exist in multiple states at once, and entanglement, where particles can be instantaneously connected regardless of distance, force us to rethink the very nature of time, space, and causality. In the context of thermodynamics, Planck's work also had far-reaching consequences. The idea that energy is quantized challenged the classical view of energy conservation, leading to new developments in the field of statistical mechanics. Planck's work demonstrated that the classical notion of temperature, which had been based on the average energy of particles in a system, was incomplete. Instead, temperature had to be understood as a more intricate relationship between the energy states of individual particles. This new framework helped bridge the gap between classical and quantum views of thermodynamics, providing a more complete description of the behavior of matter at both large and small scales. The ramifications of Planck's discovery were not just theoretical. The quantization of energy has practical applications in a wide variety of fields, from medicine to communication technology. One of the most well-known applications of quantum mechanics is in the development of semiconductor devices, which form the basis of all modern electronics. The operation of a transistor, for example, relies on the quantum mechanical properties of electrons. Likewise, lasers, which are used in everything from fiber optic communication to surgery, depend on the controlled emission of photons, a concept that traces its origins back to Planck's work on quantized energy. As scientists continue to explore the strange and counterintuitive world of quantum mechanics, they are still grappling with many of the questions that Planck's discovery first raised. How do we reconcile quantum mechanics with general relativity, the theory that governs the behavior of gravity on a large scale? How can we explain the role of consciousness in the collapse of quantum states? These questions are still open to interpretation, and they form the subject of much ongoing research in the field of theoretical physics. The search for a unified theory that can bring together quantum mechanics and general relativity remains one of the most profound challenges in modern science. Max Planck's insight into the quantization of energy remains one of the most profound and influential discoveries in the history of science. His work set the stage for the development of quantum mechanics, a theory that not only transformed our understanding of the microscopic world, but also led to the creation of technologies that have revolutionized our daily lives. Today, we continue to build on Planck's work, exploring the boundaries of what we know about the universe and discovering new realms of possibility. Planck's legacy is a testament to the power of human curiosity and the enduring nature of scientific progress. In conclusion, Max Planck's introduction of quantized energy was the starting point for a new era in physics, one that would radically change the way we understand the universe. His ideas formed the basis for quantum mechanics, which continues to shape both theoretical physics and practical technology. Planck's work has had a lasting impact on science, leading to breakthroughs in everything from electronics to medical imaging, and his legacy lives on in the many technological advancements and new discoveries that continue to emerge from the quantum revolution. Planck's ability to think beyond the confines of classical physics allowed him to see the world in a new light, and his work remains one of the cornerstones of modern science. Max Planck's work in quantizing energy had far-reaching consequences that extended beyond the specific problem of blackbody radiation. The implications of his discovery reshaped the entire landscape of physics and led to the development of one of the most successful theories of the 20th century, quantum mechanics. While Planck's initial insight was focused on resolving a technical issue in thermodynamics, it paved the way for an entirely new understanding of the microscopic world, one that would challenge classical ideas and forever alter our approach to the laws of nature. The birth of quantum theory, spurred by Planck's concept of quantized energy, opened the door to new theories, experiments, and technological advancements that continue to shape science today. In this part, we explore the broader impact of Planck's work on the development of quantum mechanics, its influence on future scientific discoveries, and the way it has reshaped our understanding of reality. Planck's quantization of energy, his discovery of Planck's constant, and the mathematical framework he introduced were the starting point of a revolution in physics that would result in a completely new framework for understanding the physical universe. The journey to quantum mechanics began with Planck's radical proposition that energy could not be emitted or absorbed continuously, but instead existed in discrete packets or quanta. Planck introduced the constant times h asterisk, which was crucial in describing the relationship between the energy of radiation and its frequency. Planck's formula E equals h dot c dot f established that the energy of radiation is proportional to its frequency, a groundbreaking idea that had never been considered in classical thermodynamics. This idea was crucial in resolving the ultraviolet catastrophe, a paradox that arose in classical physics when attempting to describe the spectrum of radiation emitted by a blackbody at high frequencies. Planck's insight that energy could only exist in discrete amounts went against the very foundations of classical physics. Classical mechanics, developed by Isaac Newton and others, operated under the assumption that energy was a continuous variable, meaning it could take any value within a given range. Planck's hypothesis that energy could only exist in quantized units was a stark contrast to this view, and initially, many scientists were hesitant to embrace it. It was only after Planck's ideas gained further experimental support, notably through the work of Albert Einstein and others, that the concept of quantized energy began to gain wider acceptance. In the years that followed, Planck's quantization idea evolved into the broader theory of quantum mechanics. One of the key developments in the theory was the understanding that the properties of matter and energy at the atomic and subatomic level were governed by probabilistic laws rather than deterministic ones. This was a fundamental shift from classical mechanics, which treated the behavior of objects as predictable based on initial conditions. In quantum mechanics, however, the behavior of particles could only be described in terms of probabilities, governed by a mathematical framework known as wave functions. This framework was developed further by physicists such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, who would expand on Planck's original ideas. One of the most influential developments that grew out of Planck's work was Niels Bohr's model of the atom, which incorporated Planck's concept of quantized energy. In 1913, Bohr proposed that electrons in an atom could only occupy specific energy levels, and that they could absorb or emit radiation only when transitioning between these levels. This was a direct application of Planck's concept of quantization, and it successfully explained the discrete lines in the hydrogen spectrum, which could not be explained by classical physics. Bohr's model also introduced the idea that these energy transitions were governed by the same rules that Planck had used to describe blackbody radiation. As the theory of quantum mechanics developed, another important concept that emerged was wave-particle duality. This idea, first introduced by Albert Einstein in his explanation of the photoelectric effect in 1905, stated that light and other forms of electromagnetic radiation could exhibit both wave-like and particle-like behavior. Einstein's work on the photoelectric effect confirmed Planck's hypothesis that light, too, is quantized and consists of discrete particles known as photons. This concept of wave-particle duality would go on to become one of the cornerstones of quantum mechanics and was instrumental in the development of quantum field theory. The work of Werner Heisenberg and Erwin Schrödinger further refined the theory of quantum mechanics. Heisenberg's uncertainty principle, introduced in 1927, stated that there is a limit to how precisely we can know certain pairs of properties of a particle, such as its position and momentum. At the same time, this uncertainty was not a limitation of measurement tools, but rather a fundamental feature of the quantum world. Schrödinger, on the other hand, developed a wave equation that described how quantum states evolve over time. Schrödinger's equation was a key element in the development of quantum mechanics and provided a way to calculate the behavior of quantum systems over time. The probabilistic nature of quantum mechanics, which emerged from Planck's work, led to the development of new statistical methods and mathematical models to describe the behavior of subatomic particles. In particular, the concept of wave functions, which describe the probabilities of where a particle might be found, became central to quantum theory. The wave function is a mathematical tool that encodes all the possible states a particle could be in, and its evolution is governed by Schrödinger's equation. The probabilistic nature of the wave function means that, instead of determining the exact position or momentum of a particle, We can only calculate the probability of finding it in a particular state. While Planck's work focused on the quantization of energy in the context of blackbody radiation, the implications of his discovery extended far beyond that. Quantum mechanics, the theory that arose from Planck's initial insight, has had a profound impact on the development of modern science and technology. The theory has been central to the development of technologies such as semiconductors, lasers, and magnetic resonance imaging, MRI, which rely on quantum principles for their operation. Quantum mechanics has also played a crucial role in the development of fields such as quantum computing, where researchers are exploring the potential of quantum states to process information in ways that classical computers cannot. One of the most significant contributions of quantum mechanics to modern physics is the development of quantum field theory. Quantum field theory is the framework used to describe the interactions between particles and fields, and it has led to the creation of the Standard Model of particle physics. The Standard Model, which describes the fundamental particles and forces in the universe, is one of the most successful theories in physics and has been experimentally confirmed in countless experiments. It is based on the principles of quantum mechanics and provides a unified framework for understanding the behavior of particles at the smallest scales. The development of quantum mechanics also had profound philosophical implications. The probabilistic nature of the theory challenged our classical intuition about the nature of reality and the limits of human knowledge. The idea that particles do not have definite properties until they are observed, known as the observer effect, led to debates about the role of consciousness in the collapse of the wave function. These debates continue to this day, with various interpretations of quantum mechanics, such as the Copenhagen interpretation and the many worlds interpretation, offering different views on the nature of reality. In conclusion, Planck's work on the quantization of energy was the catalyst for the development of quantum mechanics, a theory that has fundamentally changed our understanding of the universe. Planck's insights into the discrete nature of energy led to the development of a new framework for describing the behavior of particles at the atomic and subatomic scales. This framework, which includes key contributions from scientists such as Bohr, Einstein, Heisenberg, and Schrödinger, has not only transformed our understanding of the microworld, but also led to the creation of technologies that have revolutionized modern life. Planck's work continues to influence the fields of physics, chemistry, and engineering, and his legacy lives on in the technologies and discoveries that continue to shape our world today. Max Planck's revolutionary contribution to physics introduced the quantization of energy, a concept that altered the way scientists understood the very fabric of the universe. Building upon Planck's insight, quantum mechanics evolved into one of the most powerful and influential theories of the 20th century. Planck's work, particularly his equation relating energy to frequency, formed the bedrock upon which many key developments in modern physics were built. The three concepts that stand out in the progression of quantum theory, the quantization of energy, the birth of wave-particle duality, and the probabilistic nature of quantum mechanics, provide a detailed picture of how Planck's discovery led to a complete transformation in our understanding of the microscopic world. The initial step in the journey of quantum mechanics begins with Planck's introduction of the quantization of energy. His breakthrough idea arose from the desire to resolve the problem of blackbody radiation, a puzzle that had plagued scientists for decades. According to classical physics, a blackbody, an idealized object that absorbs and emits radiation across all frequencies, should emit an infinite amount of radiation at short wavelengths. This ultraviolet catastrophe stood in stark contrast to experimental results, where it was found that radiation levels dropped at higher frequencies, as if some force was preventing energy from being emitted continuously. Planck's insight was to propose that energy could only be emitted or absorbed in discrete packets, which he referred to as quanta. The key to Planck's solution was the realization that the energy of each quantum was directly proportional to the frequency of the radiation. He expressed this relationship with the formula E equals hc.f, where times E times represents the energy of the quantum, asterisk h times is Planck's constant 6.626 times 10, -34 joule seconds, and times f times is the frequency of the radiation. This equation, though simple, was revolutionary. It showed that energy could no longer be viewed as continuous, but as something that exists only in discrete amounts. This idea fundamentally contradicted the classical view of the universe, which relied on the notion of continuous energy. Planck's proposal set the stage for the development of quantum theory, even though he himself did not fully appreciate the implications of his discovery at the time. What was truly remarkable about Planck's work was that it went beyond simply solving a theoretical issue with blackbody radiation. The concept of energy quantization had profound implications for the way scientists would understand matter and energy at the most fundamental level. Planck had given birth to a new way of thinking about the universe, one that was governed by discrete, quantized units rather than continuous processes. His work not only solved the problem of blackbody radiation but also opened the door to the entire quantum realm, which would come to be defined by probabilistic rather than deterministic laws. Planck's insight laid the foundation for later advancements in quantum theory, particularly the idea of wave-particle duality. This concept was first proposed by Albert Einstein in 1905 when he explained the photoelectric effect. In this experiment, light shining on a metal surface would cause the emission of electrons, a phenomenon that classical wave theory could not explain. Classical physics suggested that the energy of light should be spread out across its wavefront, but the experimental data showed that light of a certain frequency was required to eject electrons, regardless of its intensity. Einstein's interpretation of the photoelectric effect was grounded in Planck's quantization of energy. He proposed that light itself must be quantized, existing as discrete particles which he called photons. This was a direct extension of Planck's quantization, and it demonstrated that light behaved both as a wave and a particle, a fundamental idea known as wave-particle duality. Wave-particle duality was a major departure from classical physics, where particles and waves were considered distinct entities. Instead, quantum mechanics introduced the idea that both matter and energy exhibit properties of both particles and waves. Light, for instance, could be described as a wave, but when interacting with matter, it behaved as if it were composed of individual particles. Similarly, particles like electrons, which were traditionally seen as particles, also exhibited wave-like properties, as demonstrated by the famous double-slit experiment. This experiment showed that electrons passing through two slits would create an interference pattern on a screen, much like waves do, even though electrons are typically considered particles. The realization that matter could exhibit both particle and wave properties challenged the classical understanding of the universe and provided one of the core principles of quantum mechanics. Wave-particle duality was essential for the next major concept in quantum theory, the probabilistic nature of particles. Classical physics was built on the idea of determinism, the belief that the state of a system at any given time could be precisely determined if we knew all the forces acting upon it. For example, if we knew the position and velocity of a ball, we could predict exactly where it would go next. Quantum mechanics, however, shattered this deterministic worldview. Planck's work had shown that energy could not be continuous, but existed in discrete units. This idea paved the way for the development of a completely new way of thinking about particles, one that incorporated probability rather than certainty. In quantum mechanics, the position, momentum, and other properties of particles are not fixed but instead exist in a state of probability. This idea was formalized by Werner Heisenberg in his uncertainty principle, which stated that it is impossible to simultaneously know both the position and the momentum of a particle with perfect precision. The more accurately we measure one property, the less precisely we can measure the other. This uncertainty is not due to imperfections in measurement, but rather a fundamental feature of the quantum world. Heisenberg's uncertainty principle showed that at the quantum level, particles do not follow predictable, deterministic paths, but instead exist in a state of indeterminacy where their properties are governed by probabilities rather than certainties. The probabilistic nature of quantum mechanics is captured in the concept of the wave function, introduced by Erwin Schrödinger. The wave function is a mathematical expression that encodes all the possible states a particle could be in. Instead of predicting the exact position of a particle, the wave function provides the probability of finding it in a particular location. This represents a fundamental shift in how we understand the physical world. Rather than treating the universe as a collection of deterministic objects, quantum mechanics presents a picture in which particles exist in a superposition of states, with each possible state having a certain probability of being realized when the particle is observed. The concept of superposition, where particles can exist in multiple states simultaneously, further complicates our understanding of reality, highlighting the strange and counterintuitive nature of the quantum world. Max Planck's work was the cornerstone of these developments in quantum theory. Without his initial insight into the quantization of energy, the entire framework of quantum mechanics would not have been possible. Planck's quantization of energy not only solved the problem of blackbody radiation, but also opened up entirely new avenues of exploration in physics, leading to the creation of wave-particle duality and the probabilistic nature of quantum mechanics. These developments revolutionized our understanding of the microworld and led to a host of new discoveries and technologies. The consequences of Planck's work continue to influence modern science, from the development of semiconductors and quantum computers to the exploration of the fundamental nature of reality itself. In conclusion, Planck's quantization of energy set the stage for the development of quantum mechanics, a theory that transformed our understanding of the universe. The three key concepts that arose from his work, the quantization of energy, wave-particle duality, and the probabilistic nature of quantum mechanics, provided a new way of looking at matter and energy. Planck's discovery was the spark that ignited a revolution in physics, and his legacy continues to shape the field to this day. Quantum mechanics, with its strange and paradoxical principles, has not only transformed the way we think about the universe, but also led to technologies that have revolutionized modern life, from electronics to medicine to computing. Planck's work remains one of the most significant contributions to science, and its impact will continue to be felt for generations to come. Max Planck's insight into energy quantization, which he introduced as part of his solution to the blackbody radiation problem, marked the beginning of a profound shift in the field of physics. This shift, which laid the foundation for the development of quantum mechanics, began with a radical departure from classical physics. Planck's discovery that energy was not continuous but instead existed in discrete packets, quanta, opened the door to an entirely new way of understanding the microscopic world. His work fundamentally challenged the classical, deterministic worldview that had dominated science for centuries and introduced a probabilistic framework that has become the cornerstone of modern physics. The impact of Planck's work extends far beyond its initial application to blackbody radiation, influencing every branch of physics from atomic theory to the development of modern technology. The first major consequence of Planck's work was the birth of quantum mechanics, a new theory of physics that sought to explain phenomena on the atomic and subatomic scales. Classical physics had assumed that energy was continuous and could be divided into arbitrarily small amounts. This view was adequate for macroscopic objects, but when it came to explaining the behavior of light and matter on the atomic level, classical physics failed. The problem of blackbody radiation, in particular, illustrated the shortcomings of classical theory. Classical predictions suggested that a black body would emit infinite energy at short wavelengths, an outcome that was clearly at odds with experimental data. Planck's insight that energy was quantized provided a way to reconcile these discrepancies. He proposed that electromagnetic radiation could only be emitted or absorbed in discrete amounts, each proportional to the frequency of the radiation. This idea, which came to be known as the quantization of energy, was groundbreaking. For the first time, it suggested that the continuous nature of energy was an illusion, and that the energy levels of atomic systems were restricted to discrete values. The mathematical formula Planck introduced, E equals hse.f, showed that energy and frequency were linked in a way that was not previously understood. Planck's constant *h* became a fundamental feature of quantum mechanics and played a pivotal role in understanding the behavior of particles at the atomic scale. This idea of quantization did not just solve the problem of blackbody radiation, it laid the groundwork for the entire field of quantum mechanics. Though Planck did not initially understand the full implications of his work, his discovery paved the way for other scientists to develop a new theory that would explain the behavior of matter and energy in ways that classical mechanics could not. Albert Einstein, for example, used Planck's idea of quantized energy to explain the photoelectric effect, where light shining on a metal surface caused the emission of electrons. Einstein proposed that light, rather than being a continuous wave, was composed of discrete packets of energy, which he called photons. This idea was a direct extension of Planck's work and was key to understanding the particle-like properties of light. The next major concept to emerge from Planck's work was wave-particle duality, which was first articulated by Einstein in his explanation of the photoelectric effect. In classical physics, waves and particles were considered distinct entities, each with its own set of behaviors. However, quantum theory introduced the idea that energy could exhibit both wave-like and particle-like properties. This was a radical departure from classical thinking, and it led to the development of the concept of wave-particle duality. Light, for instance, could be described as a wave, but when it interacted with matter, it behaved as though it were composed of discrete particles, photons. Similarly, particles like electrons, which were traditionally viewed as matter, also exhibited wave-like properties. This was confirmed by experiments such as the famous double-slit experiment, which showed that particles could create interference patterns, a behavior typically associated with waves. Wave-particle duality became one of the key features of quantum mechanics and has since been applied to particles at all scales, not just light. The concept of wave-particle duality also played a central role in the development of the probabilistic nature of quantum mechanics. Before Planck's work, physics was largely deterministic, meaning that the behavior of physical systems could, in principle, be predicted with perfect accuracy if all the initial conditions were known. In classical mechanics, if we knew the position and velocity of an object, we could calculate exactly where it would be at any given moment in the future. Quantum mechanics, however, introduced the idea that the behavior of particles at the microscopic level is inherently probabilistic. Rather than following deterministic paths, particles exist in a state of uncertainty, where their position and momentum are governed by probabilities. This idea was formalized by Heisenberg's uncertainty principle, which states that it is impossible to simultaneously know both the position and momentum of a particle with complete precision. The more accurately we measure one property, the less precisely we can measure the other. This was a radical shift in our understanding of the physical world, as it suggested that at the quantum level, particles do not have definite positions or velocities until they are measured. The uncertainty principle had profound implications not only for how we understand particles, but also for how we understand the nature of reality itself. It challenged the deterministic worldview that had dominated science for centuries and introduced a new way of thinking about the universe, one that embraced uncertainty and indeterminacy. Heisenberg's uncertainty principle was not just a philosophical abstraction, it had practical implications for how scientists approached measurements at the atomic scale. It meant that there were fundamental limits to how precisely we could observe the behavior of particles, and this in turn affected our ability to understand the physical world. This uncertainty was not due to limitations in measurement tools or techniques, but rather a fundamental feature of the quantum world. The idea that particles exist in a state of indeterminacy, where we can only describe the probability of finding them in a particular state, represented a complete departure from the certainty and predictability of classical physics. The probabilistic nature of quantum mechanics is also encapsulated in the concept of the wave function introduced by Schrödinger in his wave equation. The wave function is a mathematical description of the quantum state of a system, and it encodes the probabilities of finding a particle in a particular location or state. Schrödinger's wave equation describes how the wave function evolves over time, providing a probabilistic framework for understanding the behavior of quantum systems. Unlike classical mechanics, where the position and velocity of a particle can be predicted with certainty, quantum mechanics provides only a set of probabilities for where a particle might be found. The wave function, therefore, provides a statistical description of reality, rather than a deterministic one. Planck's discovery of energy quantization initiated a series of developments that completely transformed our understanding of the universe. His work was the catalyst for the development of quantum mechanics, a theory that challenged classical physics and led to the creation of a new framework for understanding the behavior of matter and energy. Quantum mechanics has since become one of the most successful and widely accepted theories in physics, providing a deep understanding of the atomic and subatomic worlds. It has also led to the development of countless technologies, from semiconductors and lasers to quantum computers and medical imaging techniques. The probabilistic nature of quantum mechanics, which emerged from Planck's work, has not only revolutionized physics but also reshaped the way we view the nature of reality itself. In conclusion, Max Planck's work on the quantization of energy was the beginning of a new era in physics, one that would lead to the development of quantum mechanics and revolutionize our understanding of the universe. His idea that energy is quantized provided the foundation for wave-particle duality and the probabilistic nature of quantum mechanics. These developments, which challenged classical physics, have since led to countless breakthroughs in science and technology. Planck's work was the first step in a journey that continues to shape the course of modern physics and our understanding of the physical world. Max Planck's introduction of energy quantization represented the dawn of a new era in physics, revolutionizing our understanding of the universe at its most fundamental level. His work was pivotal in leading to the development of quantum mechanics, a theory that would transform both theoretical and applied physics. Planck's quantization of energy, while initially an attempt to resolve a specific issue with blackbody radiation, had profound consequences that stretched far beyond that one problem. The concepts of quantization, wave-particle duality, probabilistic behavior, and the uncertainty principle became key components of the quantum world, each shaping our view of the universe. The quantization of energy was the first major leap in modern physics. Before Planck, classical physics assumed that energy could be absorbed or emitted in a continuous flow, a model that worked well for macroscopic objects but failed to explain certain phenomena at the atomic and subatomic levels. Planck, however, proposed that energy was not continuous but existed in small, discrete packets, which he called quanta. This hypothesis arose when he was trying to solve the problem of blackbody radiation, a situation in which objects, when heated, emit radiation. Classical physics predicted that, at high frequencies, the intensity of this radiation would become infinite, but experimental results showed otherwise. Planck resolved this paradox by introducing the concept that energy was quantized. His formula, E equals hc.f, where times E times is the energy of the radiation, asterisk h times is Planck's constant, and times f times is the frequency, revealed that the energy emitted by a blackbody was restricted to discrete units. This simple yet profound insight laid the groundwork for the development of quantum mechanics. As Planck's work laid the foundation for quantum theory, one of the most significant advancements was the birth of wave-particle duality. This concept emerged from the realization that light, which was traditionally considered a wave, could also behave as if it were composed of particles. Albert Einstein built on Planck's ideas in 1905 to explain the photoelectric effect, where light striking a metal surface causes the emission of electrons. In this experiment, light was shown to be quantized, with electrons being emitted only when the light reached a specific frequency. Einstein's work demonstrated that energy could be both a particle, photons, and a wave, a duality that contradicted the classical view that particles and waves were separate and distinct. The wave-particle duality concept not only explained the behavior of light but also set the stage for a broader understanding of matter itself, as even particles like electrons could exhibit wave-like properties under the right conditions. The third pivotal development in quantum theory was the shift from determinism to probabilism. Classical physics operated under the assumption that, if you knew all the forces acting on an object, you could predict its behavior with certainty. However, quantum mechanics, influenced by Planck's quantization, introduced the concept that particles do not follow predictable paths. Instead, they exist in a state of probability, where their exact position and momentum are governed by likelihoods, not certainties. This radical departure from classical determinism was formalized by Werner Heisenberg's uncertainty principle. Heisenberg demonstrated that it was impossible to measure both the position and momentum of a particle with absolute precision at the same time. The more precisely one of these properties is known, the less precisely the other can be determined. This inherent uncertainty, unlike anything classical physics had considered, was a fundamental feature of the quantum world, introducing a probabilistic framework that describes the behavior of particles in terms of likelihoods rather than certainties. Finally, the uncertainty principle, one of the most famous and influential ideas to arise from quantum mechanics, highlighted the limitations of our knowledge about the quantum world. The principle stated that there is a limit to how precisely we can measure pairs of physical properties, such as a particle's position and momentum, simultaneously. This limit was not due to imperfections in measurement tools, but was an intrinsic feature of the quantum realm. It challenged the very idea of an objective reality, suggesting that the act of measurement itself influences the state of the system. The uncertainty principle, introduced by Heisenberg, implied that at the quantum level, particles do not have definite properties until they are measured. This uncertainty formed a key part of the quantum worldview, which was radically different from the deterministic approach of classical physics. In conclusion, Planck's work on the quantization of energy marked the beginning of a new chapter in the history of physics. It set the stage for the development of quantum mechanics, which introduced groundbreaking concepts such as wave-particle duality, probabilistic behavior, and the uncertainty principle. These ideas revolutionized our understanding of the microscopic world, showing that the behavior of particles is governed by probabilities and uncertainty rather than strict determinism. Planck's insights not only solved a specific problem in blackbody radiation but also paved the way for the broader quantum revolution, which continues to shape the course of modern physics and technology today. Max Planck's discovery that energy is quantized was a groundbreaking moment in the history of science, marking the start of the quantum revolution. Planck proposed that energy could only be absorbed or emitted in discrete packets, or quanta, rather than in a continuous flow as classical physics had assumed. This insight came when he was attempting to resolve the long-standing problem of blackbody radiation, which classical theory failed to explain. Blackbodies, which absorb all radiation and emit it at various frequencies, were predicted by classical theory to emit infinite amounts of energy at high frequencies. However, experimental data showed a finite amount of radiation. Planck's solution, introducing quantization, explained this discrepancy and was the first step toward the quantum theory that would transform our understanding of matter and energy. Following Planck's quantization of energy, the concept of wave-particle duality emerged, particularly through Albert Einstein's work on the photoelectric effect. Einstein expanded on Planck's quantization hypothesis by showing that light, traditionally considered a continuous wave, could also exhibit particle-like properties. In his 1905 paper, Einstein proposed that light was made up of discrete packets of energy, which he called photons. This idea was crucial in explaining the photoelectric effect, where light striking a metal surface caused the emission of electrons. Einstein's work provided solid experimental evidence for Planck's quantization and established that not only light, but all matter and energy could have dual characteristics, behaving as both particles and waves. This duality would later become a foundational concept in quantum mechanics. The next key development in quantum theory came with the introduction of probabilistic behavior at the atomic level, a concept that departed sharply from classical determinism. In classical physics, objects were thought to have definite positions and velocities at any given time, and their future behavior could be precisely predicted. However, quantum mechanics, inspired by Planck's work, revealed that particles like electrons do not follow fixed trajectories. Instead, their behavior is governed by probabilities, with their exact position and momentum never fully determined. This concept was formalized by Werner Heisenberg's uncertainty principle, which stated that one cannot simultaneously measure both the position and momentum of a particle with absolute accuracy. The more precisely one property is measured, the less precisely the other can be determined. This principle introduced a fundamental indeterminacy into the quantum world, replacing the deterministic view of classical physics. The uncertainty principle's impact extended beyond theoretical physics to how we think about the nature of reality itself. Heisenberg's idea suggested that the universe at the quantum level does not adhere to the strict rules of classical physics. Instead of precise values for properties like position and momentum, particles exist in a range of possibilities until they are observed. The act of measurement itself influences the system, a concept that appends classical notions of objective reality. The uncertainty principle was revolutionary in that it challenged the deterministic worldview, suggesting that uncertainty and probability are inherent in the fabric of reality. Finally, Schrödinger's wave function became a cornerstone of quantum mechanics, offering a way to mathematically describe how particles exist in multiple states simultaneously, a phenomenon known as superposition. The wave function encodes the probabilities of where a particle might be found or what state it might be in. Schrödinger's equation, which describes the evolution of this wave function over time, became the mathematical backbone of quantum mechanics. Unlike classical physics, where an object's state can be determined by its exact position and velocity, quantum mechanics introduces a statistical description of nature. A particle's properties, such as position or momentum, are not fixed but are instead represented by a range of probabilities. Schrödinger's work, along with Heisenberg's uncertainty principle and Planck's quantization of energy, helped lay the foundation for understanding the quantum world, where the behavior of matter and energy defies the certainty and predictability of classical physics. In conclusion, Planck's discovery of quantized energy marked the beginning of quantum theory, setting the stage for a series of groundbreaking developments in physics. Wave-particle duality, probabilistic behavior, the uncertainty principle, and Schrödinger's wave function each contributed to the creation of quantum mechanics, a theory that fundamentally changed our understanding of reality. These key ideas, grounded in Planck's initial insight, have shaped the course of modern physics and continue to influence scientific research and technology today. Max Planck's pioneering work on the quantization of energy remains one of the most profound breakthroughs in modern physics. His introduction of the concept that energy is emitted or absorbed in discrete packets, or quanta, not only solved the problem of blackbody radiation but also set the foundation for the development of quantum mechanics. Planck's work, specifically his equation E equals h c.f, where times E times represents the energy, asterisk h times is Planck's constant, and times f times is the frequency of radiation, showed that energy is proportional to frequency. This was a significant departure from the continuous energy models of classical physics, which had failed to account for the observed radiation spectrum of heated objects. By proposing that energy exists in specific, discrete units, Planck introduced the idea of quantization that would later serve as the cornerstone of quantum theory. The notion of quantization, while pivotal in resolving the issue of blackbody radiation, quickly expanded into a broader framework, influencing how scientists understood the behavior of light and matter. Albert Einstein extended Planck's idea in 1905 by applying it to the phenomenon of the photoelectric effect, where light striking a metal surface caused the emission of electrons. Einstein demonstrated that light, instead of being a continuous wave, behaved like a particle, carrying energy in discrete units or photons. This work confirmed Planck's hypothesis that energy could only be absorbed or emitted in specific amounts, reinforcing the idea that energy exists in quantized units. Einstein's contribution showed that not just blackbody radiation but all light could be understood through the concept of quantized energy, leading to the birth of quantum mechanics. A critical idea that emerged from Planck's work was wave-particle duality, which evolved from the findings of both Planck and Einstein. Wave-particle duality posits that particles like light and electrons exhibit both wave-like and particle-like behaviors. The photoelectric effect demonstrated the particle nature of light, while experiments like Thomas Young's double-slit experiment revealed that light and electrons also behave like waves. This duality, which defied classical physics, became one of the central pillars of quantum mechanics. The realization that particles could exhibit both wave and particle properties was revolutionary and challenged the long-held distinction between waves and particles, requiring a new framework to describe the behavior of matter and energy at the quantum level. The advent of wave-particle duality led to the development of the uncertainty principle by Werner Heisenberg in 1927. Heisenberg's uncertainty principle stated that it is impossible to simultaneously measure both the position and momentum of a particle with absolute precision. This principle directly contradicted classical physics, which was based on the assumption that both position and momentum could be measured accurately. The uncertainty principle introduced a fundamental limit to our knowledge of the quantum world, where measurement itself influences the system being observed. This concept of inherent uncertainty in quantum mechanics replaced the determinism of classical physics and brought about a probabilistic view of nature, where the exact state of a system could only be described in terms of probabilities. Heisenberg's uncertainty principle contributed to the development of the wave function, a mathematical tool introduced by Erwin Schrödinger. Schrödinger's wave function describes the probabilities of where a particle might be found and in what state. Unlike classical mechanics, which provides exact predictions for the motion of objects, quantum mechanics uses the wave function to provide a statistical description of a particle's behavior. The wave function's evolution over time is governed by Schrödinger's equation, which allows scientists to calculate the probability distributions of a particle's position and other properties. This was a radical departure from classical physics, which sought deterministic predictions and marked a shift to a probabilistic model of nature. The last key concept in the evolution of quantum mechanics was superposition, which emerged from the wave function's ability to describe multiple states simultaneously. In quantum mechanics, particles do not have definite properties until they are measured. Instead, they exist in a superposition of all possible states, and the act of measurement forces the particle into one specific state. This idea is famously illustrated by Schrödinger's cat thought experiment, where a cat in a box is considered both alive and dead until observed. Superposition, along with the probabilistic nature of quantum mechanics, led to new ways of thinking about the nature of reality, challenging classical ideas of objectivity and determinism. In conclusion, Max Planck's introduction of energy quantization ignited a series of revolutionary ideas in physics. His work not only resolved the problem of blackbody radiation, but also laid the foundation for wave-particle duality, the uncertainty principle, the wave function, and superposition, all of which would form the basis of quantum mechanics. These concepts shattered classical notions of determinism and provided a new probabilistic framework for understanding the universe at its most fundamental level. Today, the legacy of Planck's work continues to shape modern physics, offering profound insights into the nature of matter and energy. Max Planck's introduction of energy quantization in 1900 marked a monumental shift in the way scientists understood the physical universe. Planck was tasked with solving the problem of blackbody radiation, which classical physics failed to explain. Classical models predicted that an idealized blackbody would emit infinite energy at short wavelengths, a contradiction to experimental observations. Planck proposed that the energy of electromagnetic radiation is not continuous, but instead comes in discrete amounts, or quanta, directly proportional to the frequency of the radiation. His formulation, E equals hc dot F, where times E times is energy, asterisk H times is Planck's constant, and times F times is frequency, introduced the idea of energy quantization. This discovery was the first step toward the development of quantum mechanics, revolutionizing our understanding of matter and energy. Building on Planck's work, Albert Einstein expanded the idea of quantization in 1905 to explain the photoelectric effect, a phenomenon where light striking a metal surface ejects electrons. Classical wave theory could not explain why light below a certain frequency did not produce this effect, regardless of its intensity. Einstein proposed that light consists of discrete packets of energy, or photons, and only light with a frequency above a certain threshold could provide enough energy to release electrons. This groundbreaking insight not only confirmed Planck's hypothesis that energy is quantized, but also established that light exhibits both wave-like and particle-like properties, a concept that would become central to the emerging theory of quantum mechanics. The concept of wave-particle duality, introduced by Einstein's work and supported by Planck's earlier ideas, became a cornerstone of quantum theory. Wave-particle duality suggests that light and matter exhibit both wave-like and particle-like behaviors. For instance, light can be understood as a wave that propagates through space, but when interacting with matter, it behaves as if it consists of discrete particles, photons. Similarly, particles such as electrons, which were traditionally seen as matter, also exhibit wave-like properties. This duality challenged classical physics, where waves and particles were treated as separate entities. Quantum mechanics thus emerged as a new framework, in which both wave and particle models are needed to describe the behavior of matter and energy at the atomic scale. The next breakthrough in the evolution of quantum theory came with Werner Heisenberg's uncertainty principle, which formalized the probabilistic nature of quantum mechanics. Heisenberg's principle states that it is impossible to simultaneously measure certain pairs of properties of a particle, such as position and momentum, with arbitrary precision. The more accurately one property is measured, the less accurately the other can be known. This introduced a fundamental limit to how much we can know about the state of a quantum system. The uncertainty principle replaced the deterministic worldview of classical physics, where it was assumed that if we knew all the forces acting on an object, we could predict its future behavior with certainty. Quantum mechanics, by contrast, provided only probabilities, not certainties. Erwin Schrödinger's wave function further developed the probabilistic nature of quantum theory. Schrödinger proposed that particles, such as electrons, are not localized in a specific position, but rather exist as a wave of probabilities that describes the likelihood of finding the particle in various locations. The wave function, which is a mathematical solution to Schrödinger's equation, encodes all the possible states a system could be in. Unlike classical physics, where objects have definite properties, quantum mechanics provides a statistical description of the system. The wave function's evolution over time is governed by Schrödinger's equation, making it a central tool in predicting the behavior of quantum systems. The concept of superposition, which arises from the wave function, states that particles can exist in multiple states at once, and their properties are not determined until they are observed. This idea is famously illustrated by Schrödinger's cat thought experiment, in which a cat in a sealed box is both alive and dead until the box is opened and the cat is observed. This paradoxical concept challenges our classical understanding of reality, where objects exist in one state at a time. In quantum mechanics, particles exist in a superposition of all possible states, and the act of measurement forces them to collapse into one definite state. Planck's work set the stage for a new understanding of reality, one that was governed by uncertainty, probability, and duality. His ideas were the cornerstone of quantum mechanics, which later developed into a robust theory that explains the behavior of particles at the atomic and subatomic levels. Quantum mechanics has had profound implications for both science and technology, leading to advancements in fields such as semiconductors, lasers, and quantum computing. It has also challenged our fundamental understanding of nature, suggesting that at the smallest scales, the universe operates in ways that are far different from our everyday experiences. Planck's contribution was not just a solution to a specific problem in blackbody radiation, but the foundation of a new way of thinking about the universe, forever changing the course of physics.